Hello, my dear students. Today I am going to discuss high spin and low spin complex. In the previous class, we understood the crystal field theory of octahedral, tetrahedral, and square plane complexes. Now I am going to discuss high spin and low spin complexes. Before going to understand this, let us observe this picture. Let us observe this picture. So here we can found that there are two coordination complex. One is hexacyano cobalt 3 complex, hexafluoro cobalt 3 complex. In both the complexes, the central metal ion is cobalt and the oxidation state of central metal ion is +3 in both the complexes. And if you look at the electronic configuration, this is a splitted electronic configuration. See the splitted here. In the first case, the splitting is more. See, the gap is more. In the second case, the gap is less. So you try to distinguish both the configuration. Both the configuration are completely different. Their crystal field stabilization energy is the crystal field stabilization energy is more for this complex and it is less for this complex. And when we come to electronic configuration, dear students, you know how to write the electronic configuration, ordinary electronic configuration like orbital diagram. So you must able to write electronic configuration by using T2G and EG. The electronic configuration of this complex is, for example, T2G, T2G6, EG0. Why EG0? Because in T2G there are 6 electrons, that's why it becomes T2G0, and EG no electron, that's why EG0. And when you come to this complex, the electronic configuration is T2G4. There are 4 electrons in T2G level and there are 2 electrons in the EG level. That's why EG2 is the electronic configuration. You must able to write the electronic configuration by using T2G and EG. It's very simple. Write the splitted D level and fill the number of electrons. But to fill the number of electron, it's quite difficult. You look at in both the cases, there are 6 electrons. But in this case, all the 6 electron goes to T2G. But in this case, so 4 electron go to T2G and 2 electron go to EG. And you know Und's rule. What Und's rule says? Und's rule says that during distribution of electron into various available orbital, the pairing of electrons starts only when all the electrons are singly filled. This is the statement. That means during accommodation of electron, what happens? First, electrons are singly filled. For example, you remember there are 5d orbitals. 5d orbitals, dx square, dyz. There are 5d orbitals are there here. Okay. So imagine take d6 system. Here what happens? First electrons are singly filled. 1, 2, 3, 4, 5. So all the electrons are must be singly filled in all the orbitals. Then pairing start only when all the electrons are singly filled. So this is what Und's rule. Pairing start. This is Und's rule. But if you apply the Und's rule here, what happens? You just look at it, you apply the Und's rule here. So 1, 2, 3, 4, 5, 6. So the second one follow the Und's rule. This obeys the Und's rule. But here what happened? So 1, 2, 3. According to Und's rule, electron should be enter into this orbital. But instead of entering into this, so it fill in the lower energy orbitals. So this violates the Und's rule. So why it violates Und's rule? Why the second one follow Und's rule? It's very simple. You know strong ligand and weak ligand. We discussed in case of valence bond theory. So here cyanide is the strong ligand. Cyanide is the strong ligand and fluorine is the weak ligand. Fluorine is the weak ligand. What is the function of strong ligand? The strong ligand is 1. It can able to force the unpaired electrons to pair up. It can force the unpaired electrons to pair up. And the strong ligand is 1. So it is going to cause more repulsion during bond formation. So more repulsion, the energy gap will be more. So you look at here, this is strong ligand, that's why the crystal field stabilization energy is more. And fluorine is a weak ligand, the crystal field stabilization energy is weak. So here the nature of ligand play an important role. If it is strong ligand, it violates Wundt's rule. If it is weak ligand, it follow the Wundt's rule. And if it is strong ligand, you observe here there are no unpaired electron. It is going to decrease the number of unpaired electron. But if it is weak ligand, so the number of unpaired electron is more. So this is called as high spin complex. This is called as high spin complex, and this is called as low spin complex. And one thing we must understand here. So why cyanide is strong ligand? Why fluorine is weak ligand? We have to understand this. So as I said, the crystal field stabilization energy and the number of unpaired electrons depends on nature of this ligand. Here, even though the central metal ion is same on either side, here the crystal field stabilization energy, the number of unpaired electron is depends on nature of ligand. The ligand decides whether it is high spin or low spin. The ligand decides the crystal field stabilization energy. But the next question to all of you is how to calculate stabilization energy, or how the ligand is directly affecting on crystal field stabilization energy, or how to distinguish strong ligand and weak ligand, or how to identify whether it is strong or weak. These are the questions comes to your brain. So I'm going to explain the next slide. Before going to that, high spin complex is the complex, so it possesses more number of unpaired electron. Low spin means less number of unpaired electrons. Okay, before going to that, you must know the answer for this question. Okay, dear students, based on spectrochemical series, we are going to identify whether it is strong ligand or weak ligand. So spectrochemical series means what? Yes, it's a series of arrangement of ligand based on their crystal field splitting of ligand, splitting ability of ligand, because you know that the splitting of d orbital is depends on ligand, because if ligand is strong, splitting is more. If splitting is more, the crystal field stabilization energy is more. So based on the crystal field splitting of a ligand, we are going to arrange the ligand in the increasing order. That arrangement is called as spectrochemical series. But next question is how to identify the crystal field stabilization energy or crystal field splitting capacity of a ligand. This can be identified through some spectral studies. It's very simple. Through some spectral studies, you just look at here. You take these two complex. In both the complex, chromium of oxidation state +3. So in this case, you just look at the crystal field stabilization is very high for cyanide and very less for fluoride. So we are identify by using spectral studies. So what usually we are going to do in spectral studies, we are going to take the sample of this hexacyanochromium complex. And we are going to pass the light. As soon as they pass the light, so it is going to absorb some amount of light, it is going to emit some amount of light. So based on the amount of light it emitted, we are going to judge the capacity of ligand. So it's very simple. You just look at here. So here they are going to pass the light. This is a sample tube in which we are going to place the coordination complex and we are going to pass the light. Suppose if it is strong ligand, what happens? It is going to absorb more energy. If it is weak ligand, it is going to absorb less energy. See here, it is going to absorb the energy of 26,600 centimeter inverse, but it is going to absorb the energy of 15,000 centimeter inverse. Why? Because you see here, you know the concept. If we pass the energy to the substance, it's going to absorb the energy. At that moment, electron which is present in the ground state, so it will go to higher energy state or splitted d energy level, T2G and EG. So it go to EG level. and again it come back to Eg level. See, if the energy gap is more, what happens? It's going to absorb more energy. If energy gap is less, it's going to absorb less energy. Once again, dear student, so spectrochemical, as I said, spectrochemicals means it involves some spectral studies. Spectral studies means what? It involves interaction of light with matter. In order to judge whether it is strong ligand or weak ligand, take the coordination complex containing different ligand and subjected them to absorption spectroscopy. So based on the amount of light absorbed by the complex, we are going to judge whether it is strong ligand or weak ligand. If anything going to absorb more energy means what? The energy gap is more. Why it is going to absorb more energy? Because it has to travel from year to year. You see, there are two splitted energy level. You just look at here. So both cannot going to absorb same amount of energy. For this small, just observe the cursor here, dear student. For this small amount of energy is enough. For this more amount of energy is needed, absorbed. Why? Because of cyanide. So here because of fluorine. So if it is going to absorb this energy, the amount of energy absorbed during this measurement we are going to record in a suitable device. So just if you are goes on changing the ligand, you are going to get different values of absorption spectrum. So based on these values, we are going to arrange the ligands in the increasing order. The arrangement of ligands based on their crystal field splitting energy, it is called as spectrochemical series. You just look at here. So this is called as spectrochemical series. So here iodine, it's the weakest ligand. So CO, strong ligand. See here in spectrochemical series. So that is the increasing order of delta naught value. Okay, the amount of energy which is absorbed is exactly equal to what? Is exactly equal to delta, that is crystal field stabilization energy. So here, so iodine possesses less energy and carbon monoxide, cyanide, okay, these are strong ligands. Okay, here the spectrochemical series, this is the experimental fact. Valence bond theory says strong ligand and weak ligand. It does not give any experimental evidence and does not tell why it is strong and why it is weak. But crystal field theory says that, so in crystal field theory, the crystal field stabilization energies depends on ligand, and so practically they are measured by using absorption spectroscopy. They subjected various ligands or various coordination compounds possessing different ligands subjected to absorption spectroscopy. There they found that, okay, some complexes absorb more energy, some complexes absorb less energy. The principle here is the amount of radiation absorbed is directly proportional to the energy level, the splitted energy, the magnitude of splitted energy level. So more the magnitude, more energy is going to absorb. So more energy is going to absorb because the splitting is more in that case. So we can calculate the splitting just by knowing the amount of radiation absorbed. That's why they conducted spectral studies. Based on spectral studies, so they measure the value and they arrange them in the increasing order. That is called as spectrochemical series. Dear student, it's very important thing, because while discussing the stability, while calculating the crystal field stabilization energy, while deciding high spin and low spin complexes, while deciding magnetic properties, while deciding colored complexes, the knowledge of ligand is very, very important. You must be able to judge whether it is strong or weak. So we can judge whether it is, we can identify it, we can detect with the help of spectrochemical series. If you know the nature of ligand, you can judge whether it is a strongly high spin or low spin, whether it is a paramagnetic or diamagnetic, whether it shows color or not, whether it is stable or unstable. All the properties depends on nature of ligand as well as nature of a metal ion. To know the nature of a ligand, to know the strength, the knowledge of spectrochemical series is very, very important to you people. In the next class, I am going to continue these high spin and low spin complexes.